This video is all about chemical reactions. The first thing that we have to clarify when talking about this is what actually makes up a chemical change and what makes up a physical change. The simple way to think about this is a physical change does not change the molecular structure of whatever it is that we're dealing with. For example, boiling water obviously looks like we're changing it, but it's still water. We're just turning it into water vapor. Whereas on the left-hand side over there, those chains are rusting. That means they're oxidizing. Oxygen is mixing in with the atoms that are in the chain, and it's physically changing it into something else. There's nothing that you could do to take the rusty chain and turn it back into the chain that it was before. We could, however, turn that water vapor back into liquid water if we caught it and then just cooled it down. So you could collect that in a container, you could cool it down, and it would turn back into water. There's really nothing you can do, though, to reverse that chemical change that's happening on the left-hand side. So an easy way to think about this is that chemical changes are permanent, whereas physical changes are reversible. Even if you look at the container that the water is boiling in, if we were to take that and smash it on the floor, that's still a physical change, even though you might say, well, how would you reverse that? Well, you could melt the glass back down and turn it back into a beaker again. It wouldn't necessarily be easy or simple, but it's something that could be done, whereas there's really nothing that you can do to take that rusted chain and turn it back into the exact chain that it was before that. So think of a chemical change as something that's permanently reorganizing the atoms of that substance, and it's now a different material. Now, when we're talking about chemical reactions, there are ways to write this as a formula, and this breaks down into two areas. We have what are called reactants. These are on the left-hand side, and then products, which end up on the right-hand side. They're separated by an arrow which shows you the direction of the reaction. Now I'm going to show you an example of a reaction that we're actually going to spend a lot of time with as the year moves on. This is actually the process that's keeping you alive here from minute to minute. It's the process of respiration. Now, if we break this one down, we've got the reactants on the left-hand side. The first reactant is a relatively big molecule. It's C6H12O6. This is sugar. O2 is oxygen. It's the oxygen gas we're getting out of the air. On the right-hand side, this is the product side, we have CO2, which is carbon dioxide, which you're exhaling all the time, and then H2O, water molecules. These water molecules actually stay in a part of your cell called the mitochondria, where this entire process takes place. But the thing that I want you to understand out of this reaction here is we've got reactants on the left, products on the right, and then this arrow in between kind of separates those two groups. One of the things you'll notice is all the things on the right are represented on the left. These carbons eventually become these carbons. These oxygens eventually become these oxygens. So this is just rearranging the different molecules on this side in order to make what's over here. The problem is this isn't exactly a balanced reaction, because if you notice on the left-hand side, for example, we have 6 carbons, but there's only 1 carbon over here. So technically, the balanced version of this reaction is C6H12O6, it's our glucose, plus O2 yields 6 CO2, and then 6 H2O. If you have this formula, now all of the different elements add up. There's the same number of carbons on the left-hand side as there is on the right-hand side. So one of the things that you'll be responsible for this chapter is balancing chemical equations. You'll get something like this where, for example, we've got our, say, look at hydrogen. We've got 12 hydrogens over here, only 2 on this side. So what we end up doing is putting that 6 in front of it. One thing I should clarify, if we're looking at this one right over here, that is technically like doing this in math class, where you then end up distributing this 6 over the 2 hydrogen and the implied 1 by the oxygen. So 6H2O actually gives us 12 hydrogens and then 6 oxygens. You multiply it by each one of those. It would work the same way for the 6 CO2. This would give us, if we combine this together, think of it as sort of the distributive property in math. So if we're distributing this one, it's 6 times 1 gives us 6 carbons, 6 times 2 gives us 12 oxygens. The next thing for us to talk about are different reaction types. There are two main types of reactions in chemistry. Now, one of the things that I hope I've established with you well throughout the year already is the concept that a lot of this chemistry stuff is witchcraft. Because of that, we're getting some help from our favorite wizard here, Mr. Snelling. He's going to help us go through and explain some of these reaction types. Now you can see Mr. Snelling is disguised as one of our most famous and recognizable Hollywood wizards. If we're looking at the two reaction types up here, Snelling's going to help us point this out using his staff here. At the top, we have a reaction type that is releasing energy. All of you have probably done this. You light a candle. That candle is going to continue to burn and give off energy. The name for this kind of a reaction is exothermic. So if we get Mr. Snelling out of the way there, exothermic. The prefix on this one, exo, tells us things are leaving, or like exiting, or think of like an exoskeleton on an insect. It's on the outside of the body. Well, in this case, an exothermic reaction means it's giving off energy. Anyone who's ever gotten their hand a little bit too close to a candle has experienced this. It's certainly giving off energy, and you can feel that. Now, if we if we follow Mr. Snelling along down here as he points to this bottom reaction example, in this case we've got a cold pack. So maybe somebody hurts their ankle, you mash up one of those chemical cold packs, and it starts to get very, very cold very quickly. In this case, this reaction is actually absorbing energy. So let me get these exothermic guys out of our way so we don't get confused. In this example, this is actually what we call an endothermic reaction. What that means is it's absorbing energy. The prefix endo means like in or taking in. So in this case, it's absorbing thermic or thermal energy. So if you wear like a thermal base layer in the wintertime, that's to help keep you warm. So thermal's in reference to heat. In this case, an endothermic reaction is absorbing heat, which is why the cold pack makes you feel cold. It's actually absorbing the heat energy that's given off by your body. It's the same idea as if like you grab an ice cube in your hand. That ice cube is actually absorbing the heat energy, which is why it feels cold. Now the difference is that ice cube is not a chemical reaction. This is a chemical reaction that's going on inside that pack that's absorbing the energy around you. So if we get our pictures back out of the way here. Exothermic, if we follow Mr. Snelling here, the exothermic reaction is going to be one that gives off energy. So think of that as something that's hot or something that you wouldn't want to come in contact with. Endothermic is going to be absorbing energy. So we got to thank Mr. Snelling here for helping us out, everybody's favorite wizard, helping us with all this chemistry witchcraft that we have to work our way through this chapter. Got to keep your eye out for him in future videos. I think he'll be making other guest appearances in the future. Thank you for watching, and please take a minute to answer the questions after you're finished.